What's up, everyone? Welcome to Simulation. I'm your host, Alan Sakian. And as you know, we like making the complicated relatable. And so here we are sitting down with Dr. Melanie Matheu. Thanks for coming on the show.
Yeah, thanks for having me.
I appreciate it so much.
Yeah, definitely.
And Melanie is the CEO and founder of Prellis Biologics. And we're going to be diving into understanding how to print organs and tissues.
And beyond, right?
And beyond.
Yeah.
So you have a good background because you got a PhD in physiology and biophysics at
Correct.
Irvine.
Mm-hmm.
And then you were messing around with this technology and you were like, why is it not being used for 3D printing?
Exactly. Exactly.
And now you were showing me these crazy videos, which we'll show you soon, of you actually printing vascular architecture, and I mean like 5 to 10 microns thick.
Right. 5 to 10 microns in diameter.
In diameter.
Right.
Mm-hmm.
Yeah.
This is mind-blowing stuff.
Yeah. So this is tiny stuff. It's so small that a single red blood cell has to go through single file.
Single file red blood cells.
Yeah.
Oh my goodness. Those are small. Veins. That's small vasculature.
Yeah, it's the smallest vasculature in our body.
Okay.
But without it, none of the organs or tissues that keep us alive can function.
Yep.
Yeah, because you need to have tiny, tiny cell walls and the single file movement of the red blood cells to effectively distribute oxygen and then to also carry away the waste.
Yep.
Yeah.
Yeah, and that's the role of the red blood cell.
That's the role of the red blood cell and the tiny, tiny microvasculature that ferries these red blood cells around the tissue. And
So normally we're going inhale and then red blood cells carrying oxygen to different parts of the body, and then red blood cells on the way out carrying waste
products, CO2, right?
Waste and CO2 out, and then they get into this single file line in the thinnest of the veins.
Exactly.
In the thinnest diameter. And so then the complexity is like, how do you print in that small of resolution? And that's been this problem for a long time.
It's been a problem for a long time, and a lot of the lithography methods that are out there can do it, but they do lithography. Kind of the way a silicon chip is built. So you can think of it that way. And so a lot of
lithography. What is
lithography? So it's a light-based deposition of materials. Yeah. So or other methods are out there, but usually there's a photoresist and a mask. But this lithography is typically done photoresist or mask or a scanning line of a laser, which is how we imaged, and that was the technology I used. That's all too slow to build complex vasculature and tissues. It would take months to years to build anything functional. Anything that's, say, a centimeter cubed would take several weeks, if not years, to build at the resolution we need to be creating this microvasculature that functions and brings oxygen to the tissues. So
compared to what you were teaching me earlier, months is just crazy in comparison.
It's not going to work, right?
Yeah.
Right. No one's going to wait years or months upon. The cells can't wait months upon months, right? But no one's going to wait years and years for a kidney. They do on the donor wait list, but we can't build something that slowly in the lab and have it actually still work. So what we've done is we've sped up this process significantly by taking that laser, projecting it in 3 dimensions, and depositing structure kind of like Lego blocks. And so we don't have to wait for the beam to scan around. We can deposit it all at once and build the tissue very quickly that way.
Let's pull this up.
All right, so we're going to watch some videos.
This is so video.
And
the visuals help so much with understanding.
And we all kind of intuitively understand what microvasculature is. Anyone can take their fingers and press them together, and you watch them go from pink to white, and then you pull them apart, and they go pink again. And those are capillaries. That's reperfusion of capillaries. So they're really in every tissue in our body.
Okay, so as I press my fingers together,
it kind of squeezes all the blood out of the capillaries.
They're squeezing the blood out of the capillaries.
Right.
That's why it turns white, and then you let go, and the blood flows back.
Blood flows back.
Yeah.
Yeah.
Those examples are so fun because they're so relatable.
Because everyone carries it around with them.
Everyone carries it
right?
around.
You can just do this and go, oh yeah, okay, there it is.
Yeah. And that's why when you tie something really tight around your
yeah,
finger.
yeah, like when you were a kid and you'd be like,
why is it white?
Yeah,
Yeah.
Yeah, that's why.
So do they get that thin down to 5 to 10 microns? Is that like where?
Oh yeah, every tissue in the body. And the farthest space you'll ever find them in the body is only 200 to 300 microns apart, because that's the limit of diffusion for oxygen. So our whole body, every 200 to 300 micrometers apart, at a minimum, has a capillary. In our heart, because it's constantly beating, it's really metabolically active,
Yes.
they're only 20 microns apart. So that's an even tougher engineering problem.
So you're having to engineer 5 to 10 micron diameter of veins about 20 microns away from each other.
Yeah.
And that's the only way to make an actual heart.
Right, to have a metabolically active cardiac tissue.
That is mimicked to the human heart.
Exactly.
Versus engineered in well, how can we design a better heart?
Right,
that's
yeah.
a tough question in itself.
It really is.
Is this video a good one to start with?
Yeah, sure.
Okay,
That's
cool.
great.
Let's do this one.
So this is kind of an overview of how we do our printing process. So projection of laser, deposition of the vasculature system, and then we rinse out the first layer, and we can start layering in cells on top of that and around the vasculature system that's already printed.
So this is a kidney.
That's a kidney, exactly.
And so let's start here. So
All right.
this is a proprietary machine for
Right.
us that you guys made at Prellis.
Designed and hand built. Yep.
Designed and hand built, and you have a team of 8 people that
Yep.
figured out how to really make this happen. So
Yeah, I've got 3 optical engineers on
3
this.
optical engineers, and so then that's kind of this top part here. So we're looking at right up here.
You're looking at one part of it. It takes up a whole table right now.
A table, like this big of a table?
No, I'd say
big.
about double this size.
So double that size.
So that's
That
a
machine's
laser,
double that size.
the
Wow.
laser and all the free space optics. We keep it open so we can play with things and fiddle it around.
Yeah.
We can probably get it to about this size or smaller. Yeah.
Yeah, and so then the 3 optical engineers are working on this upper part, and so this upper part is what is going on with the light, and then it's it looks like it's going into like a concave shape.
Yeah, so that may be more of an artist rendering there, but really it's coming down.
It's coming
like
straight.
Pretty much straight down.
Okay.
Yeah.
Okay. Cool.
Right. So what's going on to get it that way?
Yeah.
So we start with a single laser beam. It's probably about 2 millimeters in diameter. I think it's our beam diameter, somewhere around there. We expand it out. So we take something called a beam expander, and we just make a column of light. That column of light hits something that acts like a projector. It's called a spatial light modulator. You can be thought of almost as an LCD projector type. And it has, basically it's liquid crystal based, but if you want to think about it in a very easy way, it has on-off switches, like little on-off mirrors that direct the light. And so you can turn each pixel off and on and get an image out of that, right? And so we take that light, bounce it off some spatial light modulators. We do something called phase modulation, which takes the image that we have in XY and distributes it in Z. And that's how we get the hologram projected.
Yep.
And so then we send that.
Again, you're turning on and off whichever
on-off
pixels.
Yep.
And then you're in a Z plane for the 3D.
And then we do some phase modulation and get it in the Z plane. And then we bounce it through some more proprietary systems that our engineers have built and send it down through what essentially looks like a microscope head right now. It concentrates the light, it concentrates this little picture, and on the other end, we get the full image printed.
And then is what you initially, did you put the CAD rendering in through the laser?
Yeah, so we start with a CAD image. So, you could take an image of this cup, right? Have a CAD file of it. We run it through our hologram algorithms, and those are not proprietary. They've been published, I think, since the 70s. But we run them through some hologram creating algorithms, and then run it through that system, and then it's projected as a hologram.
Okay, and then as the laser comes directly down, then the light hits the material.
Right.
And now what is the material?
So the material is, right now, it's a mixture of PEG diacrylate, polyethylene glycol. It's FDA approved once it's solidified, and some proteins, things like collagen and stuff that's natural to our body. And so things that cells are typically happy in is what we're printing with. And so we can do this process with cells present and have them survive it and have them grow.
And then once the laser hits the PEG and collagen mix, then what occurs to form? Yes.
So it's a photo cross-linking event. So anything that let me think about, it's kind of like, you can think about an epoxy curing, but it needs light to cure. And so it's a great example if you're a woman and you've ever gotten a gel manicure. I told this to a group of like women business leaders and they were cracking up. I'm like, this is the perfect audience. You all get it. But any sort of light-based solidification, that's the same reaction that we're using. And so we have a specific wavelength that interacts with a electron donor, something that absorbs that light, kicks off an electron, and causes the cross-linking reaction to occur very locally. And so that's how it works. So it's a light-based polymerization reaction. And that's kind of where we get the building life with light tagline.
Yeah. Building life with light.
Yeah.
A light-based polymerase reaction.
Yep, in 3D. And with that, we can get down to such a small resolution that we can actually build the blood vessels and capillaries that feed tissue. And no one's been able to do that fast enough to build functional tissue before.
Building life with light.
Yep.
That's such a cool tagline.
That's our tagline, yeah. Yeah, it took a few meetings to get there, but we've got some great creative people.
That's a good one, yeah, I like that a lot. Okay, and then, so as the laser comes down and hits, so then the material itself is only about, it's the 5 to 10 micron stick itself is the material on the sheet.
So that's, we can print something that's 5 to 10 microns in diameter. Our actual resolution's about half a micron in the X and Y, so about 500 nanometers. And in the Z, it's a little longer of a resolution, it's about 3 microns, but that's just because of our optics and the way physics works. That resolution, however, is only dependent on our optical system. So we could go lower in resolution, and we can go higher in resolution, higher in resolution down to about 100 nanometers. We just kind of don't need to for what we're printing, so that's the sweet spot that we chose.
And so then as the first sort of initial, you're right now you're at, Prellis is, we're not at that stage yet.
No, we're not at that stage. We're darn close.
Getting there.
We're getting there, yeah. So to print something the size of a kidney all at once, we need to step out of the realm of off-the-shelf optics. It's totally feasible, but we'll be requesting some custom large-scale optics. It'll probably be a little more expensive, but we're really close to being able to do that. There's no physical limitations around doing that.
Because, okay, you were telling me that it only takes a couple milliseconds to print the first?
Yeah, so depending on the size and the optics that are printing, we have clocked our polymerization reaction at under 5 milliseconds. And so we can, as long as we're depositing the light and distributing it properly, it's in the order of seconds or less.
An order of seconds versus the months that you were talking
about
earlier.
Right, so just scan it around. Yeah,
that's crazy.
Yeah,
these types of innovations are the ones that we thirst for to accelerate science and engineering and.
Thank you.
Yes. Okay. So we're not quite to this part yet.
Yeah.
So right now, after you print off the, is there another good video that we should?
So there's one of kind of a fun vascular structure. That's a good one.
This one?
Yeah, sure.
All right, let's do this one.
So these print videos are not sped up at all. These are real time, just so everyone knows. And this is, I think, that field of view, I think we're at about 250 microns long. And
oh my gosh.
About 10 microns in width there. And so that's just a natural vasculature bed that we kind of doodled out ourselves to mimic some stuff we'd seen in an article. We can take that image, recreate that vasculature bed in just a few seconds.
So this is exactly what it looks like. I mean, within us, this is about 5 to 10 microns. This is about 5 to 10, and then across the whole things, you said about
250 microns or so. Yeah.
And so, this is the slow. This is real time.
Yeah.
This is real time, and it's boom. That's it, and
that's
it's done.
There's our structure. Yeah.
And, wow. Holy cow.
Yeah. So it's actually an advancement in manufacturing, if you want to think about it that way. But the problem that seemed the most relevant and applicable to me as a physiologist was really getting human tissue and real solutions out to people. And so this is our first application.
And the kind of like the shine that occurs as it goes, that's the polymerase reaction.
Yeah,
what was the first word in that?
Polymerization reaction.
But what was the first word?
Photopolymerization.
Photopolymerase reaction.
Yeah.
Because the electron is...
You're kicking off an electron. Maybe I shouldn't get that detailed.
Off an electron.
Yeah.
And that's what's causing the binding of the two atoms that form the shell, that form this exterior.
Yeah.
Form the. Okay.
So you're getting a chemical linkage that's permanent.
Chemical linkage that's permanent.
Right.
Yeah. From a liquid to a solid.
Exactly. So we're printing this all in a liquid bath that reacts to a specific wavelength of light. And what we're doing is sending that wavelength in a pattern. And so it leaves that pattern behind when we turn off the light. Yeah.
Exactly.
Yeah.
Say hi to Lawrence in South Africa.
Lawrence?
Hi, Lawrence.
Yeah.
Hey, Lawrence. Thanks for tuning in.
Hi.
We appreciate it. We'd love to hear your thoughts on the video. If you got another comment, send it over. Thanks, Ron. It's always nice when people chime in online.
Yeah, that's fun. That's really fun.
It's also cool from South Africa. We had a quote from Levi. Shout out to Levi from Melbourne in Australia. 14-year-old messaged us like, "I love your channel. Like, I can't believe I found this. Like,
that's fantastic.
So it's like it's just so great. We got some Australia, some South Africa. It's good. It's good that people are tuning in from across the world because one of our things is that we care so much about youth and young people tuning in from across the world to get them inspired to build the future.
For sure.
And then now you're on here talking about let's keep getting into this 3D printing organs and tissues. So now that was the full speed. What camera was that? Do you know what we used for that?
I don't know what camera we used. I think it was an off-the-shelf like Nikon we picked up off eBay. If you're young and doing a startup, eBay's great. But no fancy camera there. That's really just the light illumination, and we have
that you can just capture with the normal camera.
We have a microscope objective underneath. And so we're watching the light come through, but it's hooked up to a normal video, just a normal like SLR-based camera.
Is there now before we keep going? Thank you. Is there another video? Thanks, Ron.
Sure. Yeah. I mean, let's see. I think you like the one where we're printing the cell encapsulation device, right?
Yeah, and that was in the other email.
Yeah, I think that was in the other email. Yeah. Let's pull that up. So again,
this is cool. The cell encapsulation device. Okay.
Well, yeah. So we can use this to encapsulate 2,000 to 3,000 cells. It may be useful in diseases where you want encapsulated cells, such as diabetes, so you can protect them from the immune system, or just make them better for transplant. And so that's one without cells present. But we routinely print these around human insulin-producing cells, and we're testing those in the lab right now. As we speak, we have an active project with that. And so the cells are alive, they maintain insulin production, and we're looking at bringing that into animal studies really soon.
And this is real time.
That's so that's real time. So that's as fast as you want to give that another go.
And you're printing you're printing this can fit 2,000 cells?
2,000 to 3,000 cells will fit in that structure. And
And how many microns?
That's about 200 microns across
200 microns
and
across.
about 250 tall.
And 250 tall, and then so then you put 2,000 cells in there, and then that encapsulates those cells, and then it enables you to run tests within those environments. For you said for diabetes
Exactly.
was one,
Yeah.
and then what's the difference between doing it here versus doing it like in vitro or something? Like why here?
Oh, why would we do it in this?
In this environment.
So this environment, it's easy for us to do things like grow stem cells in the lab. We have a collaboration where they grow IPS, pluripotent stem cells, give them all the signals to become insulin-producing cells, and then they can send them to us and we can encapsulate them. And so we have an active project doing that. And so in an in vitro environment, it's easier to just control what cell types you're getting, do all the tests to make sure that you're transplanting what you believe you are transplanting. And so the lab environment can be controlled in a way that makes everything safer. I'm not sure if I answered your question.
Okay. Well, kind of.
Kind of. Let's. Yeah, sure.
This is this is brand new. I mean, when was the last time somebody was like, "Oh, I can print you a container for 2,000 cells, and you can do whatever you want with it and test with it." So, because now you can have, if you're printing them these fast, are you already selling this and selling the vascular?
Good question. So we're starting with building tumors, small tumors from patients, so that you can test drug reactions within those tumors. And so this is
it's like
a tumor. We call them organoids. They're little mini organs.
Because they kind of function like like straight up.
Like a straight up organ,
inside the body, they're trying to like yum eat up as much as possible, and convince the body that it's normal. When you're printing, are you taking something that looks like the tumor inside of me, and then you're making that to test in outside? Yeah,
that's the idea.
Okay.
And with our technology, unlike a lot of other tumor technologies, we believe that we can. Because there are people who are growing tumor cells in little spheroids and in collagen capsules. But the way that we do this, we believe that we can maintain a patient's immune system or the native immune system that is associated with the tumor. And
how do you do that?
So we might be getting into some proprietary areas, but essentially our encapsulation technology doesn't care what cell type is there. And it's tunable so that we can build an extracellular matrix that supports those immune cells. We can really add anything we want to this formulation to a certain degree and maintain our print speeds. And so we can tune this to look like a native human tumor environment for the cells. And that should support our immune system just fine. So as we know, tumor immunotherapy and a lot of the ways that you work with the immune system to recognize a tumor as being foreign and reject it depends on activating the immune system. There isn't really a good surrogate outside of animal studies that allows you to test human tumors in their native environment. And so we'd be providing a streamlined way to do that.
Streamlined way to test tumors outside in their environment, but not in the body.
Exactly,
the body.
Right.
Okay.
And we can build them with vasculature. We can build them without vasculature. We can introduce areas of hypoxia where they're not getting a lot of oxygen. That's a tricky.
That's interesting.
Problem in tumor immunotherapy, right?
Totally.
Yeah.
Because then hypoxia. So then, if you're introducing hypoxia, then you're able to run the tumor under different circumstances and test to see if maybe some hypoxia could work inside the body as well.
Exactly. Right.
Interesting. So that's the first cell.
Yeah. So we have an active partnership doing that right now with another company, and investigating that. So we've got a pilot project, and it's looking good so far.
And that's like you're printing a couple of these tumor casings per day, or
so took, what did that take? I think 7 seconds or so to print one of those. And so our structures are similar to the one that you just played on the screen, but they can print a little bit faster, and we're working on distributing the light in parallel. And so we'd be printing anywhere from 25 to 100 at once.
Yeah,
And so this
if
is
the light
truly
gets distributed in parallel.
Right.
Oh, that's so interesting.
Yeah, so we can take one of
Okay,
those
and that's
structures and
interesting.
print 100 at once is our goal.
And
yeah.
rather than going 100 lasers as well, you're going to take one laser and just try and
Yep.
break up that one laser
Yeah.
into the 100 different same copies.
Yeah, and so we're already doing that with our single cell encapsulation, and it
then-
works. Yeah.
Okay, but now that means like 25 or 100 per every like 10 seconds, and then that means like
Thousands.
thousands per day.
Yeah.
Okay, and then are you able to run with that flow right now? Like you're getting 1,000 a day? Like somebody
We're
wants.
not quite at 100 a second or every 10 seconds yet, and that's really dependent again on the optics and the laser power.
Yeah.
And so our next step was we placed an order for a really nice custom, basically print head. You could think of it as a 3D print head, but
Okay.
it's a large objective. Microscope objective with the right organization, the right settings to keep our resolution the same, but increase our field of view. And so first we increase the field of view, and then we need to match that with some laser power. So every time you break up the laser into, let's say 100, you have a drop in power, right? So in order to get the same printing to occur, you need to up the laser power. And so we have that installed, and we're just waiting on the custom objective.
You're making awesome leaps and bounds in the technology as well. So it's not.
We have a really nimble team. I love it. Yeah.
That's crucial because
Yeah.
now you're making advancements in hardware. You're making advancements in software. You're making advancements in what exact products you're making for different sectors
Right.
that are important. So you're like, you're really augmenting the project. You have some interns coming in from Stanford this summer.
We've got Stanford interns. True Ventures, who funded us, has a really great intern program.
Sweet.
Yeah, and so we got a couple interns from them, and then a really ambitious girl from UC Berkeley is coming in, and
Nice.
just a good team. Yeah.
And so you're going to be up to 12 then total.
Up to about 12
over
this
the
summer. Yep.
Oh man,
It's fun times. We're having a good time.
I mean, I hope anyone tuning in that likes biotech and that is really passionate about, or optics is.
Optics,
really
we've
important.
got, So we're doing something really fun. We're combining physiology, biophysics, optical engineering, computer science. There's a lot of code that's being written to do all this faster.
Yep.
We're introducing some computer vision, so
Yep.
we can select different populations of cells and groups and be intelligent about the way we do that as we print. And then mechanical engineering, really. So once we have 10,000 or 20,000 of these tumor organoids, how do you recover them, right? How do you do that efficiently in a way that's a true manufacturing process? So
Wow.
everything from biology to mechanical engineering, we've got it, and we've got this really nice, diverse team of PhDs that are excited by these problems, and we move quickly.
I love the fusion of all of the different
It's fun.
like fields.
Oh, it's so
into
fun.
one.
Chemistry too. We've got
Yeah.
some chemistry in there. Yeah.
Soon some blockchain.
Oh, of
Soon
course,
some-
right? Yeah. So I've got to figure out now how to add blockchain and have all of our servers mine Bitcoin when they're not running holograms.
Yeah.
Right? Okay.
So
That's actually our business model. We want to know. Okay.
now, before I ask a couple other questions, is there another piece of content that you think is important to
Let's
highlight?
see. I think those really show
So the
a lot
main
of what
ones?
we do. Yeah.
Okay. Cool.
Yeah.
All right. So then, what I wanna ask now is, we did a good amount of understanding, kind of like where you're at and how it's working out right now, and how like multidisciplinary it is to actually put it together and make it work, and where it's actually being used right now, and how that's happening. How many years would you say you're out from the kidney?
How many years out? So I get this question a lot, and people would love to hear that it's just around the corner. I will say with definitive confidence that we are closer than we've ever been in human history, because solving the microvasculature problem is critical for building a kidney.
Yeah.
Not only does it supply the kidney with oxygen, but our entire filtration system is based on capillaries. There are about 12 miles of capillaries in a human kidney.
In a kidney?
One kidney. And so the fact that we couldn't ever build those before was prohibitive, right? We could kind of maybe build mechanical filtration systems that was outside the body, maybe some you'd implant, but those have their own inherent problems. Building a real human kidney, I would love it if we can keep the speed and the efficiency that our team is working at right now and build it in, I would say, 3 to 5 years.
Gosh,
Yeah.
that sounds
We're
so
close.
right around the corner.
We're
really.
close, yeah.
Dang.
And the nice thing about a kidney is you don't need to have a full human kidney to get someone off dialysis.
How
You
do you
need-
get someone off dialysis?
They-
What do you need to
They
do
need
that?
about 20%, 10 to 20% are the numbers, the range. It's not well agreed upon when I've talked to the specialists, but that's about the range of kidney function you do need to get someone off dialysis. Our kidneys, if you kind of make a fist, that's about the size of your kidney.
And
but
the heart is also
about that size, yeah. So you've got 2 of those, maybe a little bigger.
Some
And-
of us have 5.
Right, some have 5. Actually, kidneys are an interesting organ. Again, the numbers aren't well recorded, but somewhere in like 10% to 5% of people have abnormal kidneys or a third kidney, which
Wait.
is really interesting. Yeah.
You're not pulling my leg.
No.
5 to 10%
people have these like
of people have 3
U-shaped
kidneys?
Well, don't quote me on that number. That's
Around
around there. Yeah.
Holy cow.
Some people have these U-shaped kidneys that are joined in the middle, and they never.
they're joined in the middle.
Yeah, they never know until they get a CAT scan or a full body
They never
scan.
knew.
Yeah, because it's
Oh, wow.
the kidneys function normally that way, and it's a great transplant target because
Yes,
it's,
Ron?
If you need
It's so flexible,
a
yeah.
volunteer, I got my Uncle Joe on kidney dialysis.
Oh,
He'd be more than
yeah.
happy to step up to the plate and test out your new.
I immediately
kidney.
thought
Good.
about Uncle Joe when she said dialysis.
Uncle Joe. Uncle Joe. He's a good guy.
There's such a huge need for this.
This is
It's
fascinating.
well over 600,000 people are on dialysis, have catastrophic kidney failure.
It's a
In the
part-time
US.
job.
In the US, yeah.
Kidney dialysis is a part-time job.
It is a
It's
part-time job.
exhausting. Yeah.
He said that Uncle Joe was going in twice a day or once a day for 2 hours?
I think it was
something
3 times a week, if I'm not
2
mistaken.
to 3 times a week sounds about right.
like
yeah.
for a couple hours though.
Right.
Yeah.
Like it's a 3, so that's like that's like 8 hours.
It's
something
a part-time
week.
job,
Yeah,
and
yeah.
then a lot of patients on dialysis report being exhausted afterwards. It really it takes a lot out of you physically, because it's not our natural process. You just lose a lot of energy out of it.
Okay, now walk us through what it would be like to if you only needed 10 to 20% of an actual kidney
Yeah.
to replace a kidney that needs dialysis.
Right.
Right. So what does that look like to do the whole like replacement process?
Yeah. So kidney. I'm not a transplant expert, so I may misspeak here.
You will
I
one
need to
day
be one.
become
Yeah.
one,
We've got a great transplant consultant who's signed up as an advisor. So maybe I'll double check with him next time before I come online. But as far as I understand it, you don't remove the diseased or non-functional kidney, but you kind of graft in the new kidney underneath into the blood supply. And so it's actually a very straightforward transplant surgery. It was the first transplant surgery ever done, was a twin-to-twin kidney replacement. And
How long ago was that?
gosh, I should have checked some numbers. I believe it was in the 50s.
Okay, that's what I thought.
I
like
think so,
70
yeah.
years ago or so.
Yeah,
Okay.
it was quite a while ago, and it was the first successful example of an solid organ transplant. And
Look at where we're at today.
look at where we are. It's amazing. 97% of people who get a kidney transplant 5 years later, that's still a functional kidney. It's a great transplant.
The expiration date is 7 years, though. Is that what I understand? That,
Yeah,
my Aunt Lorraine
Right,
has
right.
had a kidney for.
You know, it's really interesting.
Aunt Lorraine.
Yeah.
Aunt Lorraine.
It depends on the transplant. It depends on the health of the original kidney going in. It depends on the person's immune system. There's a person at UCSF who I think got a kidney transplant from his mother, and 30 years later, it's still going strong. It's really dependent on a few other factors. We hope that if we can use a person's own cells or a perfectly matched donor, imagine donors not having to give up a whole kidney, but a sample of tissue.
Yeah.
Right?
Yeah.
And we can grow those cells
A
in
lot
the
more
lab.
donors then. Yeah.
everyone's a donor then.
Then, yeah.
It's really easy. You just, a patch of skin or a small biopsy.
Yeah.
If you're a perfectly matched donor, you can give someone their lives back
Yeah.
without, giving up one of your own organs.
Kidneys,
Yeah. So the idea there is hopefully if we're using either a perfectly matched donor or someone's own cells, that the kidney will engraft and be healthier, that you won't have to be on really powerful immunosuppressants, which have their own set of side effects. And hopefully.
Okay,
crossing.
this is exciting. Is that the first market then for you guys? Is as you're doing this tumor outside the body. What else?
So that would be our first market we approach, where we'll really have to have deep and long discussions with the FDA.
Yeah.
Right, and important discussions, because we want to do this.
Clinical testing.
Lots of clinical tests. We want to do this right.
Yeah.
The good thing is that it's such a well-known surgery that if we put a kidney in and it doesn't quite work, but we've built everything else sufficiently.
That's a good point. Like 70 years now of figuring it out.
Right.
So
yeah. So
versus it being like the brand new field. Yeah,
we don't have to reinvent the wheel in terms of how the transplant would work, as long as we have everything else done correctly. Yeah.
That's a really important part of it.
Yeah.
Okay. All right. So how does before I get into this, I want to ask about this question, because I saw you wrote it as one of the key things, which is biocompatibility. Mm-hmm. And how do we ensure biocompatibility through this process?
Very, very good question. So when I talk about what it takes to manufacture or 3D print an organ, I talk about the resolution to build the capillaries, the complexity. We want to be able to match the complexity of a human organ. The speed, of course, because we need to have cells be alive still. We need the patient to still be alive by the time we're done printing. And then biocompatibility, the one you just asked about, is really critical. So we want to be building organs and tissues that are biocompatible, obviously non-toxic to cells, because we need the cells to grow around them and create their own functional environment. The way that we're approaching that currently, well, in the printing process, we use a non-toxic printing process. We have far red laser light that doesn't cause a lot of DNA damage, doesn't cause any, as far as we can tell, to the cells. And we use that light to build with cells present. And so the printing process itself is biocompatible. We have formulations that cells can live in. And then transplantation being biocompatible is also really important. So that comes down to the materials that we're using. A lot of people will have stents implanted, cardiac valves implanted, other things that are biocompatible for years. And so we're using materials like that in combination with proteins that are naturally found in the cells or in the cellular environment. So collagen, hyaluronic acid, fibronectins, elastins, all of those are components of an extracellular matrix that help make cells kind of happy. And once you've got that down, cells are really good at...
You can't just throw a disco party for
No,
cells.
I mean, of course you can. Do they care? I don't know. Maybe we should try that.
Yeah.
Good, you're
Give them
hired.
some cake,
Yeah, I mean, we give them the nutrients, right, that they need in the oxygen. But once you get a cell in an environment where it's happy and it's functional, it's interacting with other cells properly, they start to do something really cool, which is they produce their own extracellular matrix, and they will remodel tissues as they go. And so, we all feel really solid, like nothing's happening, but the skin on you today isn't the skin that was there 10 years ago.
Totally.
This has been remodeled, developed, stem cells have come in, they've divided. And so creating the right environment for that to happen really, and giving the right physiologic cues, will really help build a functional tissue. And we hope to be at that stage prior to transplant, so we can really say, okay, these cells have taken off, they've done the right thing, they've differentiated properly, we can test that, biopsy the kidney that we have in lab, make sure it matches a human kidney, and then go from there. So that would be the production side of being biocompatible.
And so it's not only the materials that you're using, and then the laser and how it's affecting the materials, and making sure that that is able to work with actual cells. But then once it also gets put into the body, can the cells actually grow around it and have it become one with the body?
Right.
How long will it last before any degrading, if ever?
Right.
Will there be degrading?
Right. Have the body recognize its own tissue.
Yeah, and
the goal.
not as recognize its own tissue, trick the body into.
Yeah.
Yeah. Lots of trial and error and testing, and to make sure that it sticks around and that it becomes part of the body.
Yeah. Well, we can do this in animals already. We know that, and if you think about
I
it,
think George Church has done some.
George Church is doing some work in that area, absolutely. And if you think about it, it's not very different than, let's say someone, is burned on their shoulder. It's not very different than the plastic surgeon taking some skin from their leg and transplanting it to their shoulder, right? So if you use the same cells from that patient, you just happen to grow it in a different environment, but they look the same, they act the same, they talk to each other the same way, transplanting it back onto the shoulder should be, pretty much the same. That's our hunch, yeah.
Okay, so now we have a couple slightly more difficult questions, I think, a little bit.
All right, let's get in there.
Okay, cool. So we'll start digging with some of the ways that we ask questions on our show have to do with some of the ramifications of technology on our future, especially regarding maybe ethics and philosophy and things like that.
Right.
So, all right, so the easy questions,
the ones I was trained for 15
trained
years
for,
as a scientist.
Physiology,
Yes.
ethics, they go together.
Right.
Which is actually an interesting.
They should.
Yeah, because
They really should.
I learned about the Jesuit education system, and they were making people polymathic as they were leaving the Jesuit education system.
Yeah.
And I thought that was very interesting because what would it be like if a physiologist or biophysicist also took some ethics and philosophy courses as they went, and what if some philosophers and ethicists took some biophysics courses and physiology courses? And so what would the world be like then? And
it'd be a better place.
And I think you will soon be faced with this as you work with someone that's more in the transplant understanding space. I think you will also end up working with someone that's more in the ethics understanding space as well, because especially in biotech and bioengineering, this is really relevant. Okay, now here's the question.
All right.
So one of your main goals with Prellis is to eradicate suffering, is one of the goals.
Right. To give people their lives back is what we say.
Give people their lives back, yes. And so that in itself is ding, 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 one of the best possible things you can do, if not the best thing. So to eradicate suffering, give people lives back, give people more time to be creative, to be happy, to love families, all this stuff. Okay, now this also comes with human augmentation at the same time.
Right.
So it's all right, now I have a kidney that is slowly failing, and I might only be 40 or 50,
right.
But now I want the ability to purchase a Prellis Biologics kidney and to feel like I'm 18 again.
Right.
Now that process usually comes with a price, as in you've paid a lot of money to make this happen, so now I pay you a lot of money to purchase your good. Hopefully it gets to a point where it's only $10K, let's say, for a kidney.
That would be amazing.
And even better, $100 sooner or later.
I'd want to pay more for my kidney.
Okay, so let's say that ends up being what we get to in 5 or even 10 years. Let's say it's only 10K, hopefully. Okay.
Sure. Yeah.
So at the 10K mark, it is only a certain socioeconomic status can afford it. And then maybe at the $100 mark, more socioeconomic status can afford it. Where do you stand on just the ethics around augmentations being made more readily available for people of higher socioeconomic status?
It's a really, really important question, especially with a lot of things that happen in biotech, right?
Yeah.
Because R&D is expensive. First, I'll just put this out there. We're hoping that we can match the price of procurement from a donor kidney so that it would be no different at the get-go from getting a kidney donated. So that's our ultimate goal. That's our price point.
What
so
is that,
it's around 120,000.
Wow.
is the
Okay.
cost. If you needed a kidney, someone volunteered, raised their hand and said, okay, the cost of getting that kidney from that person is about $120,000.
Got it.
And that doesn't include that person's hospital stay or anything like that. That's transplant surgeon time and whatnot. So
That's our 15-minute timer.
that's our 15-minute
Thank you,
timer.
Rob.
Oh boy. Okay.
Oh boy.
So ethics questions. Good.
Yeah, yeah.
Good. There's a timer on this. Okay. Right. So that is our goal for a price point, and at that price point, we will still be making plenty. We'll still have plenty on the table to continue to do the R&D that we need to. So R&D is expensive. It's tough to get drugs out there. It's tough to develop them. They often go off patent, and then you get to do generics. So, we're not out. My opinion is that we're not out to gouge anyone for any sort of development or R&D costs. We need to cover our own costs and make these things as available as possible. And as you bring this tech to the forefront, it's expensive at first. It always is. The first therapies are always going to cost more. They're novel, there's FDA processes to get them approved. You need to do everything you can to make it safe. Totally. And that first small, lucky patient test group that it's successful in, reaps the benefits of that. And as things go offline and become generic, as you can expand manufacturing processes, all of these drive the price down significantly. And the faster we can do that, the better, really, for everyone. Yeah.
So to piggyback on that question, a question that we ask on the show a lot is, it relates to a class-based speciation. As in, although the argument about the lower socioeconomic status slowly coming up is true, the top of the socioeconomic status is growing. It's being exacerbated by technology, just super quick growth. Right. So what do you think about a speciation regarding wealth?
Speciation regarding wealth. They did not prepare me for this question in grad school. Sorry.
I love it. That should be a question in college.
It really should be, right? Because you want to think about the implications of what you're doing. Yeah. I think.
And of the way civilization is designed in
the way civilization's designed in general. So throughout history it's been that way, right? The first people to get vaccines, were not in sub-Saharan Africa, right? But technology is great because it actually spreads. I think technology is great because it spreads the capabilities to bring things like that to lower socioeconomic and underserved populations faster. Definitely. So, if we can build kidneys in the US and get them overnighted to Africa because we have better technology, or we can get the exact genotype for all the potential donors in a village and figure out who's going to be the donor, that's technology at work, and we can start to move things forward. And I think we'll be able to get real solutions to people much faster. In terms of speciation, you don't usually need. There are some people who have polycystic kidney disease who need kidneys earlier, but people don't usually need a kidney till they're in their 40s, 50s, or 60s, right? So we've got some time to figure that out for the next generation. Yeah.
We should definitely be asking this question in high school and college. And
Sorry, was that a bad answer?
No, you made the answer in the way that you crafted it relating to you.
Yeah.
And so I'm glad that you said that, because we do think it's really important to get some answers to these tough questions.
Absolutely.
What do you a quick answer to this one? What do you think about the United States working together with other countries in the world like China in terms of being able to 3D print organs and tissues? Like, how will we collaborate across borders? Well,
I think, first of all, I think we should all work together, because the US is not alone in our health problems. China's not alone in their health problems. They have an increased rate of diabetes year over year that is similar, if not surpassing, the increases in diabetes in the US, and that's type 1.
China's getting fat?
No, it's type 1. It's autoimmune.
It's autoimmune. Oh, interesting. From what? What does autoimmune usually come from?
The etiology of autoimmune disease is not well defined, and it may be different in different populations, especially in diabetes. So no one's really sure. That's one of the hardest things about this problem, is that if you're pre-diabetic and you're a little overweight, you can go to the gym and sort that out. and work through it. But with type 1, it strikes kids as young as 3 years old, and they don't know why. And some really smart people are working on sorting that out, but this is a global problem. And I think working together is the best way to solve this. I don't, kind of like my team comes from every walk of life and different educational backgrounds. We need a global population to be thinking about these problems and really put our heads together. The faster we can get solutions to people that are real, the better for everyone, right?
And then what would be an ideal way to inspire people to work across borders? Like, do you have an idea, like the geopolitical idea about how to do it?
Again, something I didn't learn in grad school. So I'm going to say something very fluffy. It's funny. I did live and work in Europe for a little while, and one thing that you learn in travel is that people really aren't very different. We all are kind of motivated and love the same things and hope for the best for our kids and our family and our friends. And it's more, I like the idea of focusing on getting the right key people who have that vision into the right place. And then I think the borders start to fall away. And I think the strife and the issues where we don't want to collaborate, they start to disappear, because when you have people who have true vision on what's better in the key places, and you can talk to them and you can start to move projects forward, then real solutions happen.
I love it.
Yeah.
All right. Let's walk you through a couple of these ending questions. These are easier, I think, than the tougher geopolitical questions.
I was having fun. I was getting into it.
Ones.
Okay.
Good. Those are two of our fields that we talk about a lot on the show: wealth inequality and geopolitics, or globalization. All right, so let's jump you into the question of, what is the most beautiful thing in the world?
Oh, all right. Again. I really, so this is going to be, from my perspective, obviously, what the most beautiful thing in the world is. I love the complexity of biology. It sounds very, kind of trite to say that, but when you start to think about the order of chemical reactions that happen in our body on a daily basis, and they happen in milliseconds, and even just what's going on inside a single cell, these complex interactions, this dance that we have to keep things alive and functioning, it's mind-blowing. It is absolutely beautiful and mind-blowing, and in a way that, it's fun to sit and look at the stars at night and say, gosh, we're so small, but there's even smaller things happening that are more complex. And I think one of my friends tweeted the other day that there are more combinations or genes in the human genome than like atoms that in the universe, right? And that's true.
I think it might be easier to understand astrophysics than to understand biology. Maybe.
Right.
Yeah.
There might be some unknowns in astrophysics, but yeah.
Yeah, there are those unknown unknowns, and then in biology.
Also in biology as well, right?
But the way that my friend showed me a biochemical pathways chart he made.
Yeah.
And then I've also seen those, how a cell works, the chemical pathways of a cell, and how a cell works.
Right.
And it's just so difficult to understand. You got to really go through the process
stunning.
of PhD physiology to even be able to be I actually can read a book and understand what they're saying here.
Right.
And so I'm happy that you said that. It's a really important.
There's chemistry involved. There's quantum mechanics involved in that. There's a ton, right? Yeah.
Holy cow.
So I think that's the complexity of that is really beautiful.
As you said that, I was thinking about what would Melanie's answer have been 5 years ago or 10 years ago, or what will your answer be in 5 years? So that's an interesting thought, is to be to think about what the most beautiful thing in the world is to a 15-year-old, to a 25-year-old, to a 35-year-old, and just seeing how it changes over your life. Because we don't even we don't quantify those answers frequently.
No, we don't. So 10 years ago, I think it would have been the same. I was getting my PhD, I was working through these problems, I was thinking about them on a daily basis. I'd already gotten a degree in biochemistry, so I'd been studying this. But as a child, I think I was fascinated by nature, and that's what really sent me down this path, right?
Yeah.
Like why does this one plant grow this way, and why does this animal do this thing? And it's kind of informed this lifelong passion of like, how do things work really in our universe, in our world? Yeah.
I'm so happy that you had that inspiration at such a young age. Like, how do we bring that inspiration to more kids across the world?
You know, paying attention.
Paying attention,
Yeah.
and having parents
And
that
curiosity.
help point in those directions as well.
Yeah.
Curiosity.
Follow your curiosities, right? Yeah.
What do you think, Ronnie?
I want to see a picture when she was a little kid.
Sweet.
Melanie
Thank
like pointing at like a tree and like some bugs.
No,
or
I think
something.
I would like catch things outdoors and like bring them in. My mom would be like, "What are you doing with that in the house?" Like,
I'm understanding how it works, Mom.
right? Like, can't you see?
You're doing beautiful things, though.
Oh,
Yeah.
thank you. I
No,
appreciate
No,
that.
thank you.
We need you. You know, keep up the good work. We're
Thanks.
all counting on you.
Oh, very kind.
That's like the secondary tagline of simulation. Like, to keep up the good work. We're all counting on you.
I like that.
Yeah. Now, okay. Next question.
Okay.
Are we alone in the cosmos?
Ooh, wow. I mean, I think the smart answer is no. But how you define alone, that's a different question, right? So, what's your definition of that? Ooh. I mean, you know, there could be a carbon-based life form, there could be a silicon-based life form, we don't know, right? So I think, you know, a lot of unknown unknowns in the cosmos, right? And really exciting research and thoughts are happening around that.
Do you think there are civilizations that are advanced that exist in the cosmos?
I'm trying to remember. There's someone had a really great math equation around this, and I can't
The Drake equation.
The Drake equation, that's right. And I'm trying to remember what the result was, because that would be the smart answer.
One out
right?
of every 5
One
stars
out of every 5. Wow.
has a habitable planet.
Has a
orbiting.
habitable planet.
Yeah.
So, an advanced civilization, you know, I don't think we should rule it out. Are they interested in talking to us? Who knows? But yeah, and then, you know, you get into other engineering problems, right? Because physics is going to be the same no matter whose advanced civilization you're talking to. So do they have the power to come say hello? Do they want to come say hello? Are they motivated even to think that way by their society? Who knows, right?
Well, will the physics change?
This is such a cool question.
Good. I'm glad you like it.
Yeah, this is awesome. All right.
So would the physics change depending on the gravitational pull on the planet?
I mean,
could the biochemistry
so the biophysics
change?
would be different.
Would
the
biophysics
biophysics
change?
would be
huh?
different,
That's
but the
interesting.
rules of physics are
the
pretty
same. Yeah.
well defined.
But the biophysics would be impacted by the gravitational pull on the planet, so the
Right.
size of it, the proximity to the star.
Right.
Interesting.
Yeah.
So that's a really important point, that the biophysics change.
Yeah.
Oh, that's so cool.
Yeah.
Okay. All right. And now our last question,
Sure.
which is, do you think that we're in a computer simulation?
Oh, no. I prefer. Oh, hi. The dressed effect we talked about earlier.
Look at how many Melanies there are. There's so many
There are a
of
few
you.
of me.
There's your digital copies. There's so many.
That is a cheap way to fund my startup.
Yeah, exactly.
Just make copies of myself. It'll be great.
It'll be great. Yeah, there's so many of me running around working.
You know, no, I don't. You know, how you decide that you're not in that really has to come down to what you believe is real in your own perception, right? So I think the human mind is very good at convincing ourselves of things. We can also, you know, we're at the point now where we're starting to make very, very convincing computer simulations. And, you know, if we happen to be in one, thanks, I'm really happy. I enjoy my life as it is. But, you know, I don't spend too much time worrying about that, honestly.
Do you find it to be a question that can expand the mind to new dimensions of thought?
Oh, absolutely, right? Yeah. So those kind of questions are really fun, right? Like, are we alone in the universe? Are we a computer simulation? You know, can we build a cell from scratch with just the right enzymes and cocktail of DNA?
Yeah.
And, you know, it's really fun because you're pushing the boundaries of our assumptions, right, in daily life and how we approach the universe, and may make us, if we stop and think about questions like that, we start to think about the world in a different way and perhaps make better decisions around certain things, right? So those are great questions. Yeah,
I'm glad that you've been enjoying these last couple of questions on the show.
Yeah, they're fun.
And like you said, I wasn't trained about that in graduate school. That's another thing that we do on the show is we bring brilliant people into other fields of thought that they might not think so much about.
Right.
Because if we can bring these brilliant scientists or entrepreneurs or educators, technologists, whoever is here on the show, into a little bit of a deeper, nuanced understanding of ethics or philosophy or geopolitics, right? All these different fields, emotion and feeling. Like scientists understanding emotion and feeling is really important for communicating their message.
Absolutely.
So this is kind of the multidisciplinary like pot of simulation that we're stirring up.
No, that's wonderful.
Yeah.
And we are not selected for our ability to communicate as scientists. Like we speak an entirely different language.
Yes, you do.
To each other,
Yeah.
right?
But then you can communicate well to audiences, but then when you go back and talk to the optics engineers,
it's totally different. Yeah. So it's we're not selected for that, and it's important to remember that as scientists, we need to cultivate those communication and message presenting skills to people who don't speak our language, because otherwise, no one's going to care about what we're doing. And it's so
vice
important.
versa, it's important for the public to have the relatability of your communication is equally as important as their inspiration to care about the science.
Right.
Yeah.
And I think it was Neil deGrasse Tyson. He said every kid is a scientist, and it is so true.
Yeah.
Every
They're
person
sitting around like beating around
like
on
how does
things
this work? They're taking apart things, and their parents are like, stop, and But cultivating that curiosity is critical to understanding our natural world. Play is a form of learning, and we need to appreciate that and encourage it and give kids, things to take apart and problems that are tough that they have to think about for a couple of days, and that cultivates natural scientists and curiosity in everyone. And I think that's just really important. Yeah. And
then also, as Neil deGrasse Tyson says, actually having the basic needs met for you so that you have enough time
to be curious.
Yes. Otherwise, you're too busy trying to make money to pay for rent and food and electricity, and you don't even have enough time to contemplate the cosmos. Yeah, to contemplate exploration and curiosity.
Yeah.
Wow. What a great way to end the show.
Very cool.
This has been such a pleasure, Melanie.
Oh, mine. My pleasure is mine.
Thank you for coming on to the show.
Thank you so much.
So much fun having you. We've learned
so much.
Being
here.
Good. Let's keep making this happen for more amazing people in your network that are impactors. Yeah. And also, wow, our minds expanded to the dimension of 3D printing organs and tissues.
True 3D printing.
Not
layer by layer, but a 3D structure all at once.
3D structure all at once, and especially at the microvasculature level. I mean, that's really small, 5 to 10 microns. All at once, not layer by layer, and then furthermore, in hopefully half a decade, we can get to kidneys.
Yeah,
that would be fantastic. And eradicate more suffering and grow Prellis Biologics. Let's see what else after kidneys, where else we can go with
Where else we're going.
So thank you.
Thank you so much.
Thanks for coming on the show. I want to thank everyone for tuning in. Thank you so much. If you guys had a good time, make sure to take the content and go share it with other people. Continue the conversation outside of here. As we always say, don't just consume, but go create with the content. So go and write about it, make a video about it, talk to other people about it. Maybe go start your own biotech or optics company or organ printing company with it. Subscribe, join the family, comment below with your thoughts, and join us on Patreon. We need to continue sustaining the studio, continue growing this so we can go and bring the content out to more people and go travel and fly people in and do all that good stuff, get more production equipment, get Ron Vargas a paycheck every once in a while, our producing partner and director over there. Much love, everyone. Thanks for tuning in, and we'll talk to you again soon. Peace.